morning. Thank you for being here today. We are Team 3 of GAN mini project. Our team members are Mr. Praveen Kumar, Mr. Deepan Raj, Mr. Surinder. And I'm excited to share with you the project on the hybrid approach for floor plan generation using GANs and autoencoders. As architects, designers, and professionals in the built environment, we understand the vital role that floor plans play in shaping the spaces we inhabit. The process of creating floor plans traditionally involves a careful balance of creativity and functionality, often requiring significant time and expertise. Our project stems from a recognition of the growing importance of generative models in streamlining this creative process. We set out with a clear objective to develop a model that not only captures the intricate details of floor plans but also introduce an elements of creativity and diversity. Today we'll take you through a journey of combining the power of autoencoders and generative adversarial networks to achieve a hybrid model capable of generating diverse and realistic floor plans. Let's delve in the motivation behind our project, the significance it holds for architects and designers, and the innovative solutions our hybrid models brings to the table. Shall we get started? All right, let's dive into the heart of our project with a comprehensive overview. Our projects revolve around the development of hybrid approach for generating for plants and utilizing the combined power of autoencoders and generative adversarial networks, commonly known as GANs. Goals of the project. Our primary goal was clear from the outset to streamline and enhance the floor plan generation process. We aim to create a model that not only reproduces the details of existing floor plans but also injects a creative element into the generation, allowing for diversity and innovation. Methodology. To achieve this, we employed a two-pronged strategy. The autoencoder, known for its capability to capture and reconstruct essential features, formed the backbone of our model. We then seamlessly integrated this with the generative adversarial network, or GAN, which introduced the crucial aspect of diversity and realism in our generated floor plans. Significance of a hybrid approach. Now, you might be wondering, why a hybrid approach? Well, autoencoder ensures the fidelity of the generated floor plans by reconstructing essential features, while the GAN adds a spice, creativity, and diversity. It's this harmonious blend that distinguishes our approach and makes it particularly powerful. So let's explore how these two technologies work in tandem to create something true, unique, and valuable in the realm of architectural design. Shall we move forward? Dataset. Let's take a closer look at the lifeblood of our project, the dataset. Ensuring the quality and diversity of our dataset was paramount to the success of our generative model. Dataset origin. Our dataset comprises a combination of original floor plan images and additional images obtained from the Robin dataset. The Robin dataset was particularly valuable as it provided a substantial variety of architectural styles and spatial layouts. Cleaning process. Now let's talk about the cleaning process. Cleaning is a critical step in ensuring that our model receives high quality input. Our team meticulously cleaned around 200 images from the Robin dataset using Photopea app. This involved several key steps: handling image quality, ensuring consistent image quality across the dataset by standardizing resolutions and addressing any issues, dealing with corrupted images, identifying and removing any corrupted or unreadable images to maintain data integrity, standardizing image sizes, resizing images to a standardized size, a crucial step for neural network training, removing irrelevant or unusable data, eliminating images that may not contribute to our learning objectives such as incomplete or heavily distorted floor plans, handling a labeling and metadata, ensuring consistency in labeling and correcting any discrepancies if our dataset included labeled information. Data augmentation. Applying data augmentation techniques to artificially increases the diversity of our dataset, ensuring data quality. Our cleaning process was designed to ensure the overall quality, consistency, and representativeness of the dataset. We aim to expose our model to a broad spectrum of architectural styles and ensuring its ability to generate diverse and realistic floor plans. Shall we move forward on the next phase of our project? Now, let's delve into core of our model, the autoencoder. The autoencoder is a fundamental component of our hybrid approach, designed to capture and reconstruct essential features of floor plans. Encoder. The first key element is the encoder. Think of encoder as the feature extractor. It takes in our input floor plan images and compresses them into low dimensional space called the latent space. This step is crucial because it distills the most important features, reducing the dimensionality of our data while retaining its essential characteristics. Latent space. The latent space serves as a compressed and abstract representation of the input floor plans. It's a low-dimensional space where the critical features are encoded. This richness of this latent space is what allows our model to understand the representation, the unique aspects of different architectural styles. Decoder. On the other side, we have the decoder. The decoder takes the information from the latent space and reconstructs an input that ideally matches the original input. It's like our model's way of saying, let me show you what the floor plan should look like based on the essential features I have learned. Role of the encoder, autoencoder. The autoencoder's primary is to learn a compressed and informative representation of our floor plans. By doing this, it is not only reconstructs the original input, but also captures the underlying patterns and features crucial for floor plan generation. Why autoencoders? Autoencoders are powerful supervised learning models widely used for feature learning and dimensional reduction. Their ability to learn a compact representation of complex data makes them an ideal choice for our project. So, in summary, our autoencoder captures the essence of floor plans, distills them into compact latent space, and then reconstructs them, providing a solid foundation of our hybrid model. Let's now move forward to explore the complementary component of our model, the GAN. Now, let's shift our focus to other key player in our hybrid model, the generative adversarial network, or GAN. The GAN component introduces an exciting dynamic by incorporating adversarial training aiming to generative diverse and realistic floor plan. Generator. At the heart of the GAN is the generator. Think of the generator as the creative mind of our model. It takes in random noise as input and attempts to generate floor plan images. But here is a twist. Instead of simply generating images, the generator is trained to create floor plans that are so realistic that they can fool our discriminator. On the other side, we have discriminator. The discriminator is a critic in our adversarial training setup. It evaluates the generated floor plans from the generator and compares them to real floor plans from our dataset. Its role is to distinguish between real and generated floor plans. The better the generator becomes, the more challenging the discriminator jobs becomes. Adversarial training. The generator and discriminator engage in a constant game of one-upmanship. The generator strives to generate floor plans that are indistinguishable from real ones, while the discriminator aims to become more adept at telling the difference. Importance of the GAN. The GAN brings creativity to our model. It introduces the variability and imagination need for our floor plan generation to go beyond bare reconstructions. The adversarial training ensures that the generated floor plans not only match the training but also exhibit a level of creativity and diversity. Why GANs? GANs have been remarkably successful in generating realistic and novel data. Their ability to learn intricate patterns and generate diverse outputs makes them perfect fit for our project. Let's proceed to see how these components come together in our hybrid model. Now that we have encountered individual components of our model, the autoencoder and the GAN, let's talk about how these components, two powerhouses, come together in a seamless dance, forming the backbone of our hybrid approach. Integration of autoencoder and GAN. The autoencoder and GAN work in tandem to create a holistic model. We have strategically connected the autoencoder to the generator of the GAN. This integration is pivotal because it allows the autoencoder to feed its learned features directly into the GAN's creative process. Benefits of hybrid integration. This hybrid integration brings out the best of the both worlds. The autoencoder ensures the generated floor plans maintain fidelity to the input data, reproducing the essential architectural features. Simultaneously, the GAN introduces creativity and diversity, allowing the model to generate floor plans that go beyond mere constructions. Why hybrid? The hybrid model leverages the strength of both architecture. The autoencoder provides a solid foundation based on learned features, and the GAN adds the imaginative touch. Now, we laid the foundation of our hybrid model. Let's dive into training process. Adversarial training, generator training. Our training process follows the concept of adversarial training, a dynamic interplay between the generator and discriminator. Generator training. The generator takes random noise as input and attempts to generate floor plans. It learns to create floor plans that are realistic enough to fool the discriminator. Discriminator training. Simultaneously, the discriminator evaluates the generated floor plans and real floor plans. It refines its ability to distinguish from real and generated floor plans. Autoencoder training. The autoencoder is trained to accurately capture and reconstruct essential features of the input floor plans. It refines its ability to create a meaningful representation in the latent space. Let's dive into the exciting part of our project, the results. On the slides, we are focusing on the realism and visual showcase of the floor plans generated by hybrid model. Here you can side-by-side comparison between the generated floor plans and the real floor plans from our dataset. We have close-up comparison between real and generated floor plans. Notice how our model reproduces architectural features, room layouts, and even details such as door placements and window configurations. The high level of detail achieved is a testament of the effectiveness of the hybrid approach. As we delve into the quantitative evolution of the model, we employed various metrics to assess its performance. On this slide, you will find a summary of key evolution metrics, including mean square error and diversity measures. These metrics provide insights into the accuracy and variety of the generated floor plans. Challenges encountered. Training time and resource requirements. Our model's training process, especially with the alternating training between the autoencoder and GAN components, posed challenges in terms to time and computational resources. Selecting appropriate evolution metrics proved to be nuanced task, while quantitative metrics offer insights that might not capture the full extent of the model's performance. Striking a balance between quantitative and qualitative assessments ongoing challenge. Despite our efforts in cleaning and curating the dataset, certain limitations persisted. Expanding and diversifying the dataset further could enhance the model's adaptability to various architecture styles. Future work. Enhancing the creativity in generation. One of our key focus for future work is enhancing the creativity of our model. This involves exploring new architectural styles, incorporating users' preference, and refining the model's ability to introduce novel floor plan designs. Thank you.